Now let's talk about isospin and probably its third component. Now uh, what we talk about the nuclear force is that this nuclear forces are charge independent. That means the force between proton is same as that of the force between proton neutron and neutron. And so to say that these nuclear forces between proton and proton neutron pair and neutron pair, all of these forces have the same magnitude. And the charge independence of the nuclear force, it basically leads to the introduction of new quantum number. And this quantum number is called as, what is the title of this subject here is isospin. So this isospin is a result of the independence of the charge of the nuclear forces. And it was symbolized as I, and it was Heisenberg who considered that proton and a neutron in a nucleus, basically, they are the two states of a single particle. There are two states of the single particle, and that particle is called as nucleon. Now, thus these protons, the proton and the neutron in the nucleus, are basically the two states of this nucleon. The two states of nucleon, they are described by isospin. They are described by the space of isospin. I mean, internal charge space, or we may call it isotopic spin, or by isobaric spin. Now, I is 2I plus 1 orientations. These are the possible orientations. Now the nucleon of this isospin, I, if I take this I is, it has 1 by 2. How much it has? It has basically 2I plus 1 orientations. These are the possible orientations in isospin space. Now the three components of this isospin that we have, so if I take this I equal to 1, this is 2 times 1 by 2 plus 1. So this is going to give me 3 orientations. So we have 3 components of this isospin. And these 3 components can be symbolized as I1, I2, and I3. And the value of I3, the third component that I'm talking about here, what it does, it distinguishes between proton and neutron. And the two states, that's proton and neutron of a nucleus, they have nearly same mass. But proton is positively charged, it has a positive charge, and neutron does not have any charge. It's a neutral particle. So hence, due to electromagnetic interaction, there is a slight mass difference between this proton and neutron. In other words, I would say that the mass of the proton is slightly different than that of mass of the neutron, and that's because of this electromagnetic interaction between these two particles. And now, taking I3 equal to plus half for proton, and taking this I3 as minus half for neutron. The value of I that we have and I3 for a given state of a particle, they can be written in Dirac notation. We can write down that in Dirac notation. So how we can write? We can write I3 ket. So the proton and the neutron, I mean, the two states of a nucleon can be written as, for proton, so it is P for proton, it is 1 by 2 and it's 1 by 2 ket. For neutron, we have 1 by 2 and minus 1 by 2. Okay, we have minus 1 by 2 for this. And similarly, if we take pi mesons with isospin I equal to 1, so this implies we have 2i plus 1 possible orientations. This is 2 times 1 plus 1 is equal to 3. So there are 3 possible orientations in the isospin space. Now, the values of I3 for the different orientations for this meson, so we can have I3, it's plus 1 for pi positive meson. It is minus 1 for pi negative meson. And it is 0 for pi 0 meson. Now let's try to figure out, let's draw these states of what we have is we have a nucleon state, and this nucleon state breaks down into 2 states. And the 2 states are a result of electromagnetic interaction. And what we have here we will have I3 states. So here I have I equal to 1 by 2. So what I'll have is plus 1 by 2 state, that's for the proton basically, and minus 1 by 2 state for the neutron. Now, similarly, talking about a pi meson, so for pi meson, we have 3 states, 1, 2, and 3. So I for meson is 1. So this is for pi meson. And this is for nucleon. Okay, so what we will have here is minus 1 by 2, that's for neutron. Oh shit, there's no minus 1 by 2. There we have plus 1, minus 1, and 0. So for plus 1, we will have pi plus meson, and for 0, we will have pi neutral meson, and for minus 1, we will have pi minus meson. And to write down the total charge, I mean the electric charge on the state of the particle, having this ket state, what ket state we have? I3 ket. For this state, to write down the charge, Q is E times I3 plus 1 by 2. So for a proton, if I take for proton, what is I3? I3 is plus half. And therefore, what will be the charge? So if it is half plus half will give us Q equal to plus E, simply. Because putting I3 equal to 1 by 2 will give us 1. Now, for neutron, what we have I3 is minus 1 by 2. And minus 1 by 2 and plus 1 by 2 will cancel. For neutron, will have a charge Q equal to 0. So the isospin, the isospin for the proton and neutron, and talking about the charge of the proton is positive, and the charge of the neutron is negative. Now let me tabulate this thing. Let me tabulate this isospin and its corresponding third component I3 that we talked about here for nucleons, mesons, and also for hyperons. So let's go with that. So what we will have the family then we'll have the particle, then we will have its antiparticle, then we will have the isospin, and then we will have the third component. So what we will have? We will have family and particle, antiparticle, isospin, and I3, third component. Third component. Now, let us start with the nucleons. So, nucleons, okay, we have proton, and its antiparticle is p bar, and its isospin is half, and its third component is plus half and minus half. Now, talking about neutron, we have antineutron, its antiparticle, isospin is half, and it is minus, third component is minus half and plus half. And now talking about mesons. So we have pi neutral, we have pi neutral bar, its antiparticle, and it has an isospin of 1, so its I3 states, its I3 state is 0. And pi positive, its antiparticle is pi negative, and its isospin is 1, and it has plus 1 as minus 1, the I3 states. So plus 1 is for the pi plus, and minus 1 is for its antiparticle. And 0 is for pi 0, and 0 is for its antiparticle. Minus 1 by 2 is for neutron, I3 component, and plus 1 by 2 is for the antineutron. And going with K plus, for K plus we have anti-K minus, it has a spin, isospin half, so we have I3 component for this K plus is 1 by 2 comma minus 1 by 2. And similarly, if we take K0, it's K0 bar, K neutral bar, and it has an isospin of half, so this is minus 1 by 2 and plus 1 by 2. Now going with sigma particles. Sigma positive, we have sigma positive bar, and its spin is, isospin is 1, and the I3 components for sigma plus and its antiparticle is plus 1 and minus 1. And similarly for sigma minus, we have sigma minus bar, and we have 1 here, and we have minus 1 and plus 1 as their I3 components. And sigma 0 bar is its antiparticle, and it has isospin of 1, and its I3 components for both of them is 0 and 0. And after this we have hyperons. We'd like to write down hyperons. For hyperons, we have lambda neutral, lambda bar, and it has a spin of 0 and 0, 0. And then we have chi minus. So this is chi minus bar, and isospin is half. So this is minus half and half. And chi positive, then we have chi neutral here. So chi neutral, then chi neutral bar, that's going to give us 1/2 is its isospin, and plus half and minus half are the I3 components for chi neutral and its antiparticle chi neutral bar, and its isospin is half, and the I3 components are plus half and minus half. Now, we have a relation here between electric charge and third component of this isospin, and isospin I3, and the baryon number. So what's that relation? Is that charge is I3, it's the third component, plus the baryon number by 2. All right. where B is the baryon number, and Q is the charge, and I3 is the third component. Now this relation is used to find the charge on each number of iso spin multiplet. Now, for example, if I say that I3 for proton, if I take it plus half, and B is plus 1. So what will be the charge in that case? So charge is going to be I3 is 1 by 2 plus 1. So that's going to be 3 by 2. So the charge that we will obtain here, the charge on the proton, I think I have committed a mistake here. So this is B by 2, so it is going to be 1 by 2. So charge of proton is not fractional, so it is 1. So using this equation of charge with baryon number and third component of iso spin, we can calculate the charge of the proton, and this charge is simply 1. And if we say for I3, now I3 for neutron, what's that? I3 for neutron is minus half. It is minus half, and its baryon number is plus 1. So what we are going to get here is Q is, so what we will have for I3, I have minus 1 by 2, and this is plus 1 by 2. The 2 will cancel, and this Q will come out to be 0. So we can say here that the net charge on the neutron is equal to 0. And similarly, suppose I take the I3 of sigma positive. The I3 of this sigma positive is 1, and the baryon number is plus 1. So what's going to be the charge of this sigma plus in view of this equation? So Q is going to be, I3 is 1 for it. This is 1 plus 1 by 2. So that's going to be 3 by 2. Okay. So that's it.